This is Physics Introduction to Dynamics lesson, and we're going to start with Newton's laws and the forces. So when we were doing our kinematics, it was always was about motion, velocity, acceleration, distance, time, but we never talked about what causes the motion. So the dynamics is the cause of the motion. So the forces are the cause of the motion, the cause of acceleration. So without the force, an object would not be moving, or an object would not accelerate. So the Newton's first law says that it's the law of inertia. The other name for the Newton's first law is the law of inertia, and it says if the body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless it is acted upon by a force. So if you can imagine in space, you kick a pebble, and the pebble will keep going and on and on and on with that initial velocity, and will never change its velocity until the force is acting on it. The same here on Earth. If you keep a pebble, if there was no force acting on it, it would keep flying forward. But because there's friction, air resistance, so the pebble will eventually stop. So this was the Newton's first law, the law of inertia. Inertia, another word for inertia is the laziness. So an object with a bigger mass is more difficult to accelerate because it doesn't want to change its state. So it has more inertia than the object with less mass. And this leads to Newton's second law. And Newton's second law says that the acceleration of an object is dependent upon two variables: the net force acting on the object and the mass of the object. So here comes the formula. Newton's second law has the formula. The force is going to be measured in newtons. So I'm going to use the letter N for newtons. And in this case, it's the net force. And I'm going to talk more about what net force means. It's the sum of all the forces acting on the object. So this symbol means sum of all the forces is equal to the mass times the acceleration of that object. And so we know, the mass is measured in kilogram. And acceleration is, we already know this part, meters per second squared. So here is a very simple example for you to look at. Let's say I have a box, and the box has a mass of, let's say 4 kilogram. And I'm going to apply the force on it. So I'm going to apply a force on it. And I'm going to call this net force. Let's say there's no friction. So your net force is equal to 20 newtons. The question is, what is the acceleration? So acceleration in this case is equal to the net force divided by the mass. So acceleration is equal to 20 divided by 4 gives me 5 meters per second squared. Now I'm going to make another example and say, okay, here is the box. And now I have the 20 Newton force acting this way. So the applied force is 20 Newton. So that means applied force. So if I apply force, I'm going to call it applied force. And in this case, I'm going to say, okay, there is a friction now. So there is a friction. And the friction force, I'm going to write Fr as friction. And the friction force in this case is 8 newtons. Then the net force will be the difference of these two forces because they are opposing each other. So the net force in this case is equal to 12 newtons and equals to the mass times acceleration. And I'm going to say, okay, it's the same 4 kilogram box, just now I have friction acted on it. So that is 4 times acceleration. And in this case, your acceleration is going to be 3 meters per second squared. Here's another thing that I want you to use to understand the actual formula. F is equal to ma. So the Newton's second law. So if I say F is equal to ma, let me show you this example. I have a box of 3 kilograms, and I have a box of 4 kilograms. And I'm going to apply the force on each box. I'm not going to neglect the friction of 12 newtons. So this one also has 12 newtons. So the acceleration for the first case is equal to the net force, which is 12, divided by mass, which is 3, gives me 4 meters per second squared. And acceleration in the second case is, again, they both have the same force acting on them, but they have different masses. So here the net force divided by the mass gives me 3 meters per second squared. And what I want you to understand with this case is that the same force acting on 2 different masses will cause bigger acceleration where the mass is smaller. So if you apply exactly the same force on 2 masses, the smaller mass will have bigger acceleration, because if you apply the same force where you have bigger mass, you have smaller acceleration. Again, if there is the same force, you have smaller mass, that will give you bigger acceleration. So this is the main concept of Newton's second law. So you have to remember that the net force is equal to ma. Bigger mass will give less acceleration. Smaller mass will give you more acceleration for the same magnitude of the force. And magnitude means how strong it is. So that was Newton's second law. And Newton's third law is for every action there is equal and opposite reaction. So I have an image right here for you. There is an elephant, stubborn elephant. He doesn't want to move, and the man is pushing on the elephant. So the force that this man applying on the elephant, where his hands feel it, is exactly the same force as the elephant applies on the man. Or another example is you are standing on Earth. So when you're standing on Earth, you're pushing on Earth with exactly the same force as Earth is pushing on you. Or you are sitting on the chair right now, so you're pushing on the chair with exactly the same force as the chair is pushing on you. Or if you're driving in the car and the bug hits your windshield, the bug will not survive it. But it does not mean that your car pushed more force on the, applied more force on the bug. The bug applied exactly the same amount of force as your car applied on the bug. It just the bug could not handle that amount of force. So that is the Newton's third law. And we're going to look at some examples right now how to use Newton's laws to solve the equations, and how we and what the different forces are, because I only told you like the net force is equal to mass times acceleration, but there are different type of forces and the formulas for those forces. So here are a few forces that I want you to know the formulas to know and understand them. One of them is going to be the force of gravity. There are 2 different formulas of force of gravity. So the one that is close to Earth, you don't have to worry what that G is equal to. So the one that is close to Earth, G, there is no concern about G for now. We're going to take the one that we know, acceleration due to gravity. So because the force is equal to mass times acceleration, G is also acceleration, it's just acceleration due to gravity, and the force of gravity is equal to mg. Then there is a friction force. The friction force is equal to mu times n. But because we don't deal with inclines, so you don't have to worry about a mass being on the incline, so the normal force is always perpendicular to the surface. And if it was inclined, then your force of gravity would always be down. So this is the force of gravity. The normal force is always perpendicular to the ground, to the surface where the box is standing. And if it was sliding down with some velocity, and maybe it had some acceleration as well, there would be also friction, if they say there is friction, unless it's frictionless. There could be another force applied. So there are different forces. So you could say, okay, I'm going to have applied force right here that is stopping the box from accelerating too much. There is friction, there is normal force that is perpendicular to the surface, and there is force of gravity. But we're not in AP physics, so we're not going to look at inclined planes. We're just going to look at the boxes on the flat surfaces. So if you have a box on the flat surface with some mass is measured in kilograms, watch additional videos that I have posted for you for description of this video, because I want you to understand the differences between the mass and the forces. So here I have the force of gravity acting on the box. And for every action, there is equal and opposite reaction. So if the box is pushing on the ground is going to push back at this mass with the same force, the normal force. And if I am pulling the box with this way, so I'm going to say, okay, there is applied force, and maybe there is a friction force. And the friction force has its own formula. So the friction force is equal to mu times n. How do I write this letter mu? It's like U with a little tail. So it's mu. So it's something like mu. And this is coefficient of friction. And coefficient of friction does not have any measurement units. It's just a proportion. So mu is just the proportion in this case of the friction force and the normal force. So here you have newtons divided by newtons. So the measurements would be equal to, will not have the units. So that is coefficient of friction. What does the coefficient of friction depend on? So the coefficient of friction depends only on two surfaces in contact. So, so if I have, let's say, metal surface and I have a box made of plastic, when you pull that plastic box along the metal, aluminum surface, you're going to have certain mu. But if it's not plastic, maybe it's a concrete, so it's going to be different contact between that plastic and concrete, so it's going to be a different mu. But maybe the box is not made of plastic, maybe it's made of wood, then it's going to be again a different mu. So there are different types of mu's. It can be a coefficient of friction, static friction and kinetic friction, and every single one of them, they have different number depending on what surface is in contact. So your mu, coefficient of friction, depends only on two surfaces in contact, nothing else. So here is the table. There are different tables for different materials. So if I have a box maybe made of steel touching the floor that is made of steel, your coefficient of friction static is 0.6 and kinetic is a little bit smaller. And I'm going to tell you the difference between them right now. So again, if your material is made of maybe grease is added to steel, so add the grease to steel contact, and then your coefficient of friction changes. Then maybe metal on ice, again, you have different coefficient of friction. Brake lining on iron, you have different coefficients of friction, and so on. So the tire on a wet pavement, you have different coefficient of friction again. And what's the difference between the static and kinetic friction? Static friction is right before the object starts sliding. So if I have an object and on the incline, but it is not sliding yet, then I have static friction holding it. So there is force of gravity, there is normal force, and the static friction is the one that is holding the box from sliding down. So why is there kinetic friction then? The kinetic friction starts kinetic. It's like kinematics. When we did kinematics, it's the motion, right? So if I have kinetic friction, here I'm sliding the box, so I'm applying some force along the surface. And when it is sliding or moving, then I have friction But in this case, I have kinetic friction, or so I have to use kinetic friction, coefficient of friction, when my box is sliding. So if it is sliding, it's kinetic. If it's stuck and not moving, then it is static friction. Here I have an example for you, and I want you to think about this one. When you drive a car, the tires and the surface in contact, in this case, do you have static friction or kinetic friction? So your car is driving on the surface, on, I don't know, asphalt or cement or the road. So is there static or kinetic friction? Pause, take a second to think about it, and then when you have an answer, then continue playing your video. So I hope you took some time to think, and I'm about to give the answer. So if you did not answer it yet and still need time, go ahead and pause it before I give the answer. And if you did take your time to think about it, I hope you said that when the car is driving on the road, it has static friction. And why is it static friction? The car is moving. When the car is moving, it is moving, but it is not sliding. So for static friction, your object should not be sliding on the ground. For kinetic friction, when you push the box and it's sliding on the ground, then it's a kinetic friction. But when your car is driving, you're not sliding. Unless you were driving too fast and you're stopping too quickly, then you have those skid marks. This is when there's kinetic friction. Also, another question. When you're walking, is this static friction or kinetic friction between your feet and the ground? And again, pause it, take your time. Which one do you think it is? I hope you said static in this case, because again, when you're walking, you're not sliding, not skidding on the ground. So I hope you said static friction. So this is the difference between static and kinetic friction. So this was about the types of different frictions, and the formula for force of friction is mu times N. And in our case, because it is always the horizontal surface, then your normal force is always going to be equal to the force of gravity. So sometimes you will see me write in the classroom or even here. So your friction force is equal to mu times, and instead of N, because the object is not accelerating up or down, so these two forces cancel each other. Or vertically they are in equilibrium, so vertical forces in equilibrium, normal force and force of gravity are in equilibrium. I can write mg instead of n, because n is cancel mg, then they're equal to each other, so I can write instead of n mg. But it's only for flat surfaces, not on incline. And the last one I want to mention, but it doesn't have specific formula, it's a pull or push. So you can pull something, you can push something, there can be tension forces. So these forces, they do not have a specific formula, you just have to derive depending on what circumstances they are. So for these forces, we're just going to use F net is equal to ma, depending on the circumstances, and then we're going to solve for wherever they ask you in the question. So again, the force of gravity has a formula, it's mg, and it's only for objects that are on the planet Earth or other planets. G is different for every single planet. Watch the video again, there's some relationship to G. Then explanation to what G is. The second force I talked about is the force of friction, and the last one is the pull-push, or it's going to be tension force. Let's look at some examples. I might need to make a second video because each video can be only up maximum to 30 minutes. So there's going to be a second video with more practice to these questions. But let's look at this one for now. So here's the first example. Sam is pulling a 5-kilogram cart of his toys. If he is applying a net horizontal force of 10 newtons on it, what is the cart's acceleration? So when they say the net force is applied, that means they don't include the friction, or maybe there is no friction. So what happens is, here is the cart. He is applying the force of, in this horizontal force, of 10 newtons. And the cart is 5 kilograms. And the question is, what is the acceleration of this cart? So I need to know acceleration. So if I solve this equation, I'm going to say the net force is equal to ma. The net force is given 10 newtons. The mass is 5 kilograms. So my acceleration is 2 meters per second squared. Then for the second question, I have Drew is pulling a 4 kilogram box with lion in it with the force of 3 newtons. So here is the box with the lion, and I have Drew is pulling with the force of 3 newtons, and then Sam is pushing on the box with 5 newtons, and the box is 4 kilograms. And in last question, I did not show these forces, but they cancel each other. There is normal force, there is force of gravity, but I'm looking at the force, but they cancel each other. Those forces cancel, so I don't have to really look at them, but I should put them on my body diagram. It's called free body diagram when you put all the forces on the object that are acting on it. So my net force in this case, they are in the same direction. So if they were in the opposite direction, I would subtract them, but they're in the same direction, and that is equal to 8 newtons and equals to mass times acceleration. So I have the net force is equal to the mass times acceleration. So it looks like acceleration here is again 2 meters per second squared. But before we move on to the next question, I want to ask you, what is the force of gravity acting on this box? So I have this box. What is the force of gravity acting on this box? So let me go back and look at the formula. So what is the force of gravity? Oh, force of gravity is mass times acceleration due to gravity. So I can say it is mg. Then the force of gravity in this case is equal to the force, mass, and g is 10. So the force of gravity is equal to 40, and force is measured in newtons. So in this question, in the second one, I also got acceleration 2 meters per second squared. I want to ask you another question, and I want you to, again, pause it if you need time to think. I'm going to tell you that the box has weight, and weight is the force. So the box has weight of, let's say, 20 newtons. What is the mass of this box? So what do you think weight means? The box has a weight of 20 newtons. What is the mass of this box? So if you paused, took your time to think, I hope you have an answer. So the weight means the same as the force of gravity. So weight and the force of gravity is the same thing and equals to mg. So, and how do I determine that one? So when you're standing on the scale, the force of gravity is pulling you with the force of gravity, which is mg. But the weight scale is pushing back on you and shows you exactly how much you're pushing on it. So the weight and the normal force is exactly the same thing. So if they tell you that the force of gravity or weight is equal to 20 newtons, that means this is mg. But g is 10, so I can tell that the mass in this case is equal to 2 kilograms. Okay, let's look at the next question. Sam is pushing on a 40 Newton wagon. And when they say 40 Newton wagon, they can say it's a brown wagon, it's red wagon, it's blue wagon, it's yellow wagon. They said 40 Newton wagon. So what do they mean that the wagon is 40 newtons? When they say 40 Newton wagon, they mean the weight, the description of the wagon is, the weight of it is 40 newtons. So if the weight is 40 newtons, that means the force of gravity acting on that box or the wagon is 40 newtons. From here, I can tell, okay, the mass is 4 kilograms. So I know the mass of this box is 4 kilograms. Then they say that he is applying 12 newtons on it. So he is applying the force of 12 newtons. But the wagon is accelerating only at 2 meters per second squared. So its acceleration is 2 meters per second squared. So what does that mean? So it's 2 meters per second squared. So I'm going to write this one. The net force, it looks like there is friction force in this case. The net force is equal to ma. The net force is the applied force minus the friction force. The friction force is going to be in the opposite direction from the applied force. So I'm going to say the net force is applied force. So it's applied force minus the friction force and equals to ma. My applied force is 12. They don't tell me what the friction force is equal to. I figure out the mass is 4, and they gave me acceleration, is 2. So if I solve this for friction, the friction is equal to 4 newtons. Okay, so I solved the first part. I found what the friction is equal to, acting on the wagon. It is 4 newtons. But then they asked me, what is the coefficient of friction between the wagon and or maybe the tires of the wagon and the ground? Well, I know the force of friction is equal to mu times n. What is my n in this case? So the normal force is equal to the force of gravity in this case, correct? They cancel each other. So I can say that the friction force is equal to 4 and equals to mu times mg, because my normal force is equal to the force of gravity. And that is equal to 4 mu and mg. This is what they were giving me, correct? They were giving me the weight of the wagon is 40 newtons. So that is the force of friction, or the force of gravity. So that is 40. So from here, if I do calculate my mu is going to be 4 divided by 40, which is 0.1. And it doesn't have units. So it's just the proportion of two forces. And I know this is probably the question that would take a little bit longer for you to understand, and I'm going to do more practices in the second video that I'm going to record right after this one. The link is going to be in the description, but I just wanted you to know that if you want to watch this explanation one more time, just rewind back and watch this explanation one more time so you understand it better. I have one more question before the video is going to be over. Here's another question before the video is over, and you want to pause and answer this question yourself. What will happen to the airplane that has all acting on its forces balanced or in equilibrium? Or what will happen to the car with the same balanced forces? So what that means, the lift force on the airplane cancels the weight force, and the thrust force is canceling the drag force. Or maybe the friction force is canceling the engine force. And maybe the normal force is canceling the force of gravity. So these two forces cancel each other, and these two forces cancel each other. Or maybe these two forces cancel each other, and these two forces cancel each other. So what will happen to the object in this case? Pause it and try to answer. Will the airplane fall? Or will the car move? So when both forces, at first it's easy. If this force cancels each other, that force, we saw this in the box, nothing happens. Not the same as in the airplane, but in this case, your net force is equal to 0 because the forces cancel each other. So if the engine force cancels the friction and the lift is canceling the weight, then the net force is equal to 0. That means it equals to ma, and that only happens when acceleration is equal to 0. So when the net force is equal to 0, or In other words, it's called in equilibrium. When forces are in equilibrium, your acceleration is going to be equal to 0. An object can move at a constant speed, but it doesn't accelerate. So that one important fact to know. That is it for this video. Watch the next one for more practices.